So my name is Neeraj, and I'm going to walk through this lesson 3 of Fast.ai. So I'll just go through the notebooks. I might go a little fast, so please stop me because sometimes I speak fast. So and if you have any doubt anywhere, let me know. So there's 3-4 notebooks. So I'll go through each of the notebook one by one. So first thing that Jeremy start. So can I start now?
I think so, yeah.
Yeah, sure. So first thing that Jeremy started in last lecture was he wanted to teach us some foundation that we asked Jeremy in one of the thread in the forum. So first thing he taught about callbacks. So basics of callbacks, what we are using Fast.ai. So he starts with the callbacks. So first thing he tells, so if you want to write a function, assume function print hi, and there's a widget in Jupyter Notebook, they're very super handy. And so if we create a button and if click that button, nothing happens. Why nothing happens? Because we have not told the Jupyter Notebook or this widget that what to do when we click something. If I run this, if you attach that function that on click you have to print hi, then if you click this click me, then it will print hi. So basically what is happening, callbacks are a function that we call when some events happen. So when we click, we are calling the function f, and that function is printing hi. So that is the basic idea of callbacks. There's some other widget and plotly library that is very handy, where you can create the JavaScript plots, very interactive. So assume we create one function, slow calculation, and that function just okay. So we added the sleep time of 1 second. So after each multiplication, square of the number, and then it adds, and then it just print the calculation. Now, if we want to do something after each addition, so we might call some callback or some function. So what we can do, we can write one function that after each epoch, you have to print awesome, we have finished the epoch. So how we can do that? We are just passing the function, and since we are passing cv and we are calling as a function here cv bracket I, epoch will go here and it will print after each epoch, awesome, we have finished epoch 0. So basically what is happening, after each event we are calling a function, that function is doing something, that's a callback. Instead of writing a 2-line function in Python, we have lambdas function, or in other libraries also, like in Scala, in other Java. So we have lambda function, that is 1-line function. That is first argument will basically be an input, another will be the output. So same thing what this function did can be done with the lambdas functions. So here again we'll get the same output. Now, if we want, instead of giving one input, if we want to change the exclamation also, instead of writing awesome, we want to write okay, I guess, or something else. So we need to pass 2 parameters, exclamation and the epoch. Now, our callback just can take one input at a time. So what we are doing, the lambda function, we are taking only one input, but we are hard coding the another input. In that way, we are getting okay, I guess, that is hard coded in our lambda function, and the other input is coming from the while calling that callback. So we are able to print okay, I guess, we have finished epoch 0. Now, but we always don't want to hard code this thing. Another way, what we can do, we can create function inside a function. Basically, we can create a one function that will take the exclamation as the input, and it will return a function. And that function will take only one input. So now when we pass make show progress nice, what will happen? This nice will go as exclamation. It will return a function. That function inner will take only epoch as a parameter, and exclamation will go as a part of make show progress. So that was nice. The same thing, instead of writing lambda function, since lambda function are same as the normal Python function, just we have to write in this form using define, And so same thing can be done and we'll get the same output. Okay. Now we can pass anything like terrific. We can pass the exclamation as terrific and we'll get the terrific as the output. And in Fast.ai, as I was saying, we use this trick a lot of times. So we should get familiar with this thing, passing a function inside a function. Now, but since we are doing this thing again and again, there's a very nice function called partial. What that function does, it will take a function as a show progress. Since we know this function, if we go up, can take two input, right? Exclamation and epoch, and but our callback only can take only one input. What partial will do, it will automatically pass this one parameter into the show progress first argument, and the second argument will come from the callback. So partial will be handy if we want, instead of writing our own make progress function, we can just do the partial, and partial will pass the first argument of the show progress function as an argument that we passed as in a partial. And since we are using Jupyter, so as we can see, when we create the F2 function from partial, it just needs one argument rather than two arguments, because partial has already passed one argument. So that was neat and that was very handy, and we should use that Jeremy was recommending. Now, since we can create the functions, callbacks as a function, we can create the class of a callback. So we can create a classes as a callback. Now, so what we can do here, we create a one class called progress showing callbacks. In that callback, we are taking input as one exclamation. So when we create when we construct the object of this class, we'll pass the exclamation and it will get attached with that object. And then since we are using a dunder call, so we can use the object of this class as a function. And when we pass the epoch parameter, it will just take the exclamation what we passed during the initialization, and it will print we have finished the epoch number. So we just, while creating the object, we pass the exclamation as just super. And while calling the callbacks, and CV is basically object of the class, but we can use it as a function because we're using a dunder call. So that was the introduction foundation for the callbacks, and that's the way we have Jeremy has created in Fast.ai. Another important thing that he taught as a foundation, we have seen a lot in Fast.ai library, star arguments and star kwargs. Kwargs are basically key word arguments, and star arguments is just arguments. So if you are passing a parameter with a named argument, then it will go into the kwargs. If you're just passing without the name, then it will go to the argument. So if we pass a parameter 3a thing, and if we see, we'll see in arguments we're getting all the without name arguments, and where we are passing the keys, and this is basically a word or value, we are getting in it as a dictionary in the kwargs arguments. What's the advantage of this? Because sometimes when we call function, we are not sure how many arguments. That function might work with one argument, two argument, depending on the number of arguments that user pass. Therefore, we'll just define the star arguments, so star kwargs or the star arguments. So as an example, if we see here, we are calling a callback. So since now CB is a class and we are using two callbacks, so this before cal is now a method of that class. So we are saying before calculations we want to do something, and after calculation you want to do something. Now if you see in before calculation method, we have defined we can pass any number of arguments, we can pass any number of keyword arguments. And though while calling this thing, we are not using anything into our functions, but user can pass anything. And though we are passing I and this value equal to result, it doesn't matter for the function because of number of arguments and a number of kwargs. So that's the advantage of using arguments in the kwargs. Now, how he is used in the next example, assume you want to use a epoch as a parameter. So here you're passing as argument, and here you're passing epoch and the val. So two arguments you're passing. So you're not using any kwargs, you're using only the arguments. And As you can see, before the iteration, we are writing this line, and after the iteration or after the calculation, we are printing this line. So that was the introduction for kwargs and args, and that is very important in Python or in Fast.ai. And we have seen, as Jeremy told, if we are used to R. In R, there's a dot. You have to ellipsis basically to pass the kwargs. And similarly, in other library, in Matplotlib, we see a lot of these kwargs and args. Now, so till now, what we are doing, till now, we were just using the callbacks to print something. Now, if we want to modify the behavior of our function or whatever the things the function was doing, and we were saying, okay, while calling that other function, we want to modify the initial function. So how can we do with this callbacks? So what we are doing, again, same thing. We're just checking whether this callback has that attribute called before calculation, or that method, basically it has that method or not. If it has, then it will call that method. If it doesn't, then it won't call. Similarly, it is checking that whether this callback has after cal method. If it doesn't have that method, it won't call. And then what we have done, so when we have defined the after cal, what we are doing here, if the validation is greater than 10, we are returning true, otherwise it will be none. Therefore, if validation is less than 10, this won't be there. It will just bypass because it will be none, it will be false. So it will keep doing the after cal, that is basically printing this. The moment the validation will be more than 10, it will break the loop. So what we have done now using the callbacks, we are able to do the early stopping. Same thing, rather than just doing early stopping, we want to change the value of the result that we were getting. So what here we are doing, if result is greater than 10, we are just returning true. It means like we are just going to, in this print loop, we are just breaking it, right? And if it is less than 3, we are just multiplying the result by 2. So that's the way we can modify the function using the callbacks, and that basically we were doing a lot in Fast.ai while we are calling the callbacks. So that was the introduction for the callbacks. The other thing that we have seen a lot in Python, that is dunder thing. So we have a lot of dunder, like in dunder init, dunder wrapper, dunder add. So those are some function that Python call that in some doing something, it will call these, it will look for these methods basically. So like for if when Python, when we create a class and we want to create the, we want to construct the object of that class, Python, or we want to initialize the object of that class, Python will look for this dunder init. If you want to add two numbers, Python basically when you write plus, Python generally, not generally, Python always look for this this add method. And you want to print something in Jupyter Notebook generally, then it will look for the wrapper dunder. So as we can see, we have modified now. So while we are calling the plus operator, Python looked for the adder dunder add, and that's the reason. And that time we are calling our addition. So we have modified the function of add. What was default should be 3, and we are getting 3.01 because we have added 0.01. And Jeremy told we should be familiar with at least these initial thing like get item, get attribute, set attribute. And so we know if in a in a list, when we just say 3 a list comma 0 bracket 0, it will basically call get item, get attribute, set attribute. We have seen in the callbacks. Initialization, delete, we know. New is basically creating a new object of a class. Enter and exit we'll see in the next notebooks. Length is when we call a length of a list. Wrapper is printing, and string is getting a string. The next important thing that we told or taught was variance and stuff. Okay, so now what is variance? So when we get a data and we want to see how variable is that data, how much variability is there in the data. So how we measure that variability? One way to measure the variability, we calculate the mean of the data, and we'll see how much far each point from that mean, and we just sum it up. If we just do that thing, we'll get the 0, because that's the way mean we are defining the mean. We just say something positive, something negative. So how can we make it not 0? One way is we can just take the modulus, or basically absolute value of that, and take the mean, or something we can take the square of that to make it positive and then take the mean. The first thing we call it variance, and another thing we call it the mean absolute deviation. And according to Jeremy, we should use more these things. Mathematicians and others will generally use variance to reduce, to simplify the calculation. So this is variance, and if we take the square root of this, why we take the square root of this? So we want to bring everything into the same unit, because if we square it, we want to take the square root to bring it to the same unit, and that we call the standard deviation. So one more thing, as in statistics, we know so basically a mean is something like mean is, we are saying mean, it's the expected value of the square of the data points minus the expected value of the mean. If we solve that equation, what will get a variance of, variance can also be written as expected value of the square minus square of the expected values. So that will be that formula will be sometime handy, rather than just calculating the mean twice. This can be done in one loop. So now till now we were measuring how my data was variable. Like I have only one variable and I want to see how much variability there in the data point in that data. And if I have two variable X and Y, and I want to see how variability, I mean, if I change the one variable, how the other variable is changing. So that we are defining as covariance. The formula is more or less same. There we are saying X minus mean and then taking the square. Here we are saying X minus expected value of X and the Y minus expected value of Y, and then the expected value of whole. So if you see this thing here, if we see, we just took the T minus T mean, U minus U mean, that is T minus mean of X axis, U minus mean of Y axis. And when we just multiply it and take the mean, we get 103. And if we generate the random number, we are saying very low covariance. Why so? Because as the definition says, the covariance is like if I increase X, how much Y will increase. I mean, whether it is related or not, and we can see it is highly related. I mean, it's like a linear function. So we are seeing high covariance. And here, if we change something in X, we are not seeing the same change into Y. That's the reason we are seeing very low covariance. And for the real number, so basically we have defined the Pearson correlation. So the issue with this covariance is like it can go from minus, any value, minus infinity to infinity. And if we want to compare two covariance, it will be difficult, because we cannot compare easily. So what we can do, we can divide this covariance by the standard deviation. So it will bring this covariance from the range -1 to 1, and we can compare things. And this we define as a Pearson correlation coefficient. And I think softmax, if you want, I can go through it, but it's just taking the exponent of the axis and then sum it up and then divide by sum of that exponentials. And we can write, if you take the log, we can write in this form. So that why we do this thing, because in the last lecture, Jeremy told to avoid this numerical instability, because since exponential is a monotonic curve, and if you have a very large number, it will shoot up to a very large number, and it will cause errors. So in that way, we just try to remain into the stable region of mathematics, during the computation. And then he taught how to use Vim. So since I have not set up Vim right now, so any doubt in this foundation, any question?
Yeah. Hey, Neeraj. Just a couple of observations. I saw Jeremy using when he says variance and standard deviation. Like,
yes,
I've seen somewhere we are using standard deviation, and somewhere we are using variance. Why is the case? Like, I have seen them using like interchangeably.
As per my knowledge, I mean, standard deviation will be in the same unit. If you just want to bring everything into the same unit, then you should use standard deviation. Otherwise, variance is just a square of the standard deviation. So it depends on the, I'm not sure where you've seen. I mean, you cannot change interchangeably for a particular problem, but yeah, if you want to just compare the two variants, you can compare the standard deviation or you can compare the variance. Both will give the same answer.
So when in general, we like when we are training, we are like one of the assumption we are making that we want to keep mean of a 0
Yes.
and a variance of 1. Is it a variance of a 1 or is standard deviation of a 1 in each layer we are trying to achieve?
So basically square root of 1 is 1. So if you keep the variance of 1 or a standard deviation of 1, both will be basically 1. So yeah.
Okay. And one quick observation with regard to the callbacks. If you go up
Yes.
a bit, in a sense, these are, I know these are the example, but in the last lecture, he was using one big class for a callback and there was a handler class.
That is, yeah, runner handler. Yes. Yeah.
So
right.
is it like,
yes. Then.
Anybody else asking question?
Yes, I have a comment. If you could go back down to the
So first, let me complete the answer of that question, Dinesh.
Yeah.
Yeah, Dinesh. Yeah. So yeah. So why we are using that handler? Basically, you're asking about this class, right?
Yeah.
So you have created a lot of callbacks, right? You created early stopping, you have created the scheduling, so many callbacks you have created, right? Now somebody has to handle that. I mean, which one to run first? Or so in callbacks you basically have defined these small, I mean, all the functions, just returning true, nothing, right? So while you are creating a callbacks, you're calling this callback as the base class, right? And you're defining those, overriding those methods, basically begin, fit, and after step, right? Now, what handler is doing, it is trying to handle all the callbacks. So it is saying, okay, which one to run first, and in a sequentially it will going to run. So now you have 10 callbacks, right? So what is going to do is going to call, see if you see this, you're passing all the callbacks here, right? And then it is going to call all the callbacks, just a loop for all the callbacks. So for CV,
so wouldn't we be calling the call in down below? Aren't we calling it in the test callback? Like, so here I just want to override before, fit, and after step. So I define the class callback, and then in test callback I'm just overriding the begin, fit, and after step. So what's the usage of the call handler itself?
Yeah. So what is happening? You have overwritten the begin, fit, right? But here you're considering only you have one callback. Assume you have 4 callbacks, right? So for each callback has a begin, fit. So you have to call each callback individually, and that callback handler is doing. If you have only one callback, you don't need this class. That's the reason in the example that we have seen, we don't have a callback handler, right? In the this. Yeah. So when you have multiple callbacks, then it is handy. So that's the reason you're passing a list of all the callbacks.
Okay.
So that handler can loop through all the callbacks in each function. So basically in the handler, we are not writing any, we are not modifying the code anyway. We're just calling the same function begin, fit. From while fitting, it will call the begin, fit. That time we'll call all the callbacks sequentially. Some callbacks might be having that method, otherwise we just pass the return. So because all the callbacks is coming from this class, so since we have defined here only, you see begin, fit, and the after step, we have not defined other methods, right? So while you're calling this begin epoch, assume what will happen to this test callback, what it will do, it will call this begin epoch method, and that will be called through this callback handler. Because some callbacks might having the begin epoch, some might not have a begin epoch. So it will be a lot of things are going on with different callbacks. So different callbacks are doing different things. So we want to call everything sequentially through this callback handler. That's the reason in the runner class, he has defined one thing called order, what to run first. So if you see while defining the callbacks through runner class, we define something called order. Okay.
He did underscore order.
Yeah. So that basically going to say you have to run that is first, then second, and third. That he's doing sorted basically. So he's sorting all the callbacks and then running sequentially.
Okay. Yeah. Thanks for that. I think it makes sense. Yeah.
Sure. So
Thank you.
what was another question?
Yes, I had a question. It's mainly a comment. If you could go down to scroll down to the bottom, look at softmax again,
Okay, yes.
please. Yeah, so the softmax is subject to numerical instability.
Right.
And there's a trick to avoid that, and that is to subtract and add the maximum of the x, maximum of the xj's to the exponent in the sum, and then all of the x's will not be too large. That's what happens when the x's are too large.
Right.
If you subtract and add back the max of all the x's in that exponent, then you have a formula that is essentially the same, but is not subject to numerical instability.
Right. Yeah, so basically we don't just, we basically divide, but since we're taking log, it becomes the addition and subtraction. We multiply and divide. So, but it is log softmax, that's the reason it becomes plus and minus, I mean addition and subtraction. So any other question?
Remind me, what was the underscore dunder call? Underscore call we used.
So if you see this method, if I go to the underscore call, yeah. So if you see when I created this class, right?
Yeah.
And when I create the CV, if you see CV is just an object of a class, right? It is not a method. It's just an object. So it can have a method. It can have its properties. Now, when we're using the slow calculation, right? Slow calculation, and there we are calling this function as CV bracket I, right?
Yeah.
This functionality on an object can be done using dunder call. If you don't write this, there will be error. So when you call the object like a method or a function,
okay,
this Python will look for this call a method basically, and it will do whatever is written in the body.
Okay, yeah, makes sense. Thank you. And one of the question I'm going to pick up from the chat. What's the difference between a callback handler and the runner?
Okay, so what Jeremy told, since in the callback we were calling CB a lot of time. So CB.begin, like the CB. So why we can't create one separate class? So in the he created a callback class and he's calling the runner inside this. So it just basically refactoring of the code that will be nice to run. So here, if you see, now we are not calling CB.cb, just saying self begin, self after prediction. So it's just the same thing of writing in a different way.
Okay. Thanks for that. And I don't think there is any other question on the chat, so you can move ahead.
Okay, thank you. So next thing that, okay, so already, so in next notebook, that was our early stopping. So he's, since he taught us callbacks in the previous notebook, so he was just teaching a new callback that is early stopping and a learning rate finders that we generally mostly or most of the time use in Fast.ai. So this is the basic stuff. Now again, here you see he's using a runner class. So he just created a callback class and passing during when he's going to set the runner, it is going to call that runner. Okay, and that is get attribute. So we should be familiar with again this gender get attribute. So when Python don't get that attribute, what Python is going to look for this method, and then what we are saying search that attribute from the runner class. Okay, so now one thing, okay, in this notebook, what he is teaching to use exception not only for error handling, but to control the loops. So basically, if you want to control the logic for logic, so control the logic. So what we have done here, we have created a 3 class from the exception based class, and we just gave different name to the same class. And so we don't want to do anything with that class. We want to use the same functionality of the exception based class, but we wanted to create 3 names. So that's the reason we just created the 3 train exception, epoch exception, and the batch exception. Now how to use it? So basically, so if you want to stop early, so what was happening, so sometime when you are saying during callback after fit, you have to do something, and it was stopping in that loop, but it was not stopping in the outside loop or something like that. So there was some error Jeremy was getting. So that's the reason he defined these exceptions. So what now we are doing is we keep doing whatever we are doing, and if somebody call for cancel batch exception, it will just go to this part and just if somebody has defined the after what we have to do after cancel batch, then we'll do that. Otherwise, just cancel the exception. This will going to do the batch exception cancel. There it will be a train exception, and similarly there will be a POC exception. So so these are the 3 exceptions we have defined. Now how to use it? So you create a learner. Now what you're doing in the test callback, after a step, you're saying if the iterations are more than 10, raise the cancel train exception. So what will happen as the moment the number of iterations is more than 10, it will go to the cancel train exception. That is batch. Okay. This here, and it will stop this this fit, and it will just come out of the loop. And if somebody has defined what you have to do after cancel train, it will do since, but in our, I think, base class, we have not defined anything like cancel what to do after that. So it won't do anything. It just come out of it. So if you can see here, after 10 epoch, it is stopped because we have defined if epochs are less than or equal to 10, just stop training. So that's a nice use of exceptions to control this for loops and the control logic. Another callbacks that already Jeremy has defined, average stats callbacks and recorder callbacks. So that is same callbacks and parameter scheduling. So those are the same thing. One thing that he is defined LR find, so that we use. So here we will define what is the maximum iteration we want to run, like maybe 100 or something, and we can give the range. Then it will just keep changing after when we start the batch, it will keep changing the learning rate. And since we know in Fast.ai we have parameter groups we have defined. So so here we are passing same learning rate, but we can pass a different learning rate for different parameter groups. And when to stop if our number of iteration is going more than the maximum iteration, or our batch loss is 10 times more than the batch loss. In Fast.ai, they are using 3 times because they are using the moving exponential smoothing. So that's the reason they're using 3 times. But so here, if we plot it, we can see if our best LR to work for, and so we stop as the moment the 100 iteration reached, or the best loss will be 10 times less than this worst loss. So that was the basic notebook. This is the way we can tune our LR finder, or the way we want to modify it, we can do it. So any question in this?
On the chat window, I don't see any question coming in. There was a question on a decorator which is dealt.
Okay, fine.
Rest, there is no question as far as this notebook is concerned.
Sure. Okay. So I'll move to the very nice notebook where we are going to train our convolution network from the scratch. I mean, we are going to build it first, and then we are going to train it. And we are going to see how the initialization is ruining our activations. So again, since Jeremy likes to combine things into one function, so since we are calling again and again that normalization on train and normalization on valids, so he just combined into a nice handy function, and we got directly our train data set and the validation data sets. And as usual, we should have a mean of 0 and a standard deviation of 1, so we are getting that. Since so when in nn.sequential is a nice way to create our neural network in PyTorch. Now, since our so what Jeremy did. So one thing what we have to do. So Jeremy defined a Lambda class where you can pass whatever function you want to pass, and it will do that thing to our that function will be passed to the forward method. So now you can, this become basically a module on your PyTorch module and an NN module, And so you can pass a function, it will return pass that function to the R axis and activation, and it will return a function of those things. So like if you want to do, and then again in PyTorch we don't have a flatten function. So what we can do, we are writing our own function called flatten. So it is just going to flatten that thing. So
just a quick question on this, the flatten function. Is this a part of a Lambda class, or is it like an independent function here?
It's an independent function, but while calling the Lambda function, we're going to pass this flatten. So while we're creating so if you see here, so we are creating a Lambda object and we're passing a flatten as a function.
Okay.
So this function will be applied here while forward.
Okay, thank you.
So we can create one more function, that is amnist. So since our data set has like batch size into 784, but we need the input as 1 is a channel and 28 by 28. So we just want to resize it. So we created two functions, flatten and the resize function, and we're passing in Lambda in both the cases. So what Lambda class is doing, it is just passing that function in a forward, just that. And we created here 4 layers, and we are going from size 8. So, okay. And one more thing, nowadays we don't use max pool or average pooling in the middle. So we generally just stride more than 2 to reduce the size. And that's the reason we are using here. No, we are not seeing any max pool or average pooling, and we are just reducing the size by 2. So that's the reason of 8 become 14, then 7, and then like that. So we have 8 kernels here. Okay, and now, okay, so one thing that Jeremy used here the kernel size is 5 by 5, and other layer we have kernel size 3 by 3. So why we are using 5 by 5? What Jeremy told. So I just took the screenshot of the slide. So what is happening here is, so you have an image of 28 by 28, and you have a kernel size of 3 by 3. So basically you're and this has only one channel. So basically at a time when you're convolving that kernel through the image, you are multiplying 9 numbers together and generating one number of that. And since you have 8 filters, so finally for that same region, for 8 kernels, you're going to generate 8 outputs. So what basically is happening here is, out of 9 inputs, you are generating 8 outputs, right? So basically, according to Jeremy, just we are shuffling the numbers. We are not learning anything. For learning, we should learn the combination of the number or something like that. But here, what is happening? We might be just shuffling the numbers. So that's the reason at the initial layer, it's better idea to use a bigger kernel size. And therefore, when we see the ResNet architecture, we see they use 7 by 7 as a filter. Kernel size, not filter. Why? Because since MNIST data or most of the images are having the 3 channels, so it becomes 27 inputs. So we are convolving at the same time as 27 inputs. And since we use 32 as a filter in the first channel, so we are going to get 32 outputs. So again, we are not learning much, because from 27 we are just generating 32. So it's therefore in ResNet or in other architecture, the first kernel size is generally bigger, and there we use 7 by 7. And here, since it's a one channel, we went ahead with only 5 by 5. So any doubt in this?
Yeah, I didn't get it. Could you go back to these slides again, please? So we have a 28 by 28 as in our image.
Right.
And are we saying if we go 3 by 3 kernel on it?
Yes.
So I got lost afterwards. So what 8 numbers are coming out of it?
8 is the number of filters. So
second?
Okay, so you have 8 filters. So you're using 8 kernels, right? So each kernel is going to give you 1 output. So 8 kernels going to give you 8 outputs.
Okay.
Okay, so what is happening? So if you see in an image, you took a kernel, you took a 3 by 3 from the image. Okay, yeah. And so basically you took the 9 numbers from the image, and you multiply with your 9 numbers in the kernels, you got 1 number as output, right?
Yeah.
Since you have 8 kernels, so you got 8 numbers as output.
Yeah.
Okay, it means from the 9 numbers, you generated 8 numbers.
Correct.
Okay, it means assume if you are instead 8, if you take 9 kernels, so basically from the 9 you generated 9. So what he's saying is basically you might have just reshuffled the numbers, right? just ordered the number. You have not learned anything, because to generate 8 from 8 can be identity mapping, right? So it means to learn the complex features, you should take a bigger thing. So that time, if you take 5 by 5, from 25 you're generating the 8. It means you must be learning some interaction of those values.
Right. Okay.
Yes, that's the reason we are using bigger size. In case of MNIST data, since you have 27 numbers, okay, and you have a kernel size. If you take as a 3 by 3 kernel size, 3 by 3 by 3, okay. So again, and you're giving 32 filters. 32 filters generally we use in the first layer. So we are generating from 27, 32 outputs, right? So again, we are not learn, because we are expanding the. I mean, it's difficult to explain, because this question was asked again from the Jeremy. So it was just you're not learning much representation of those 27 numbers. Better if you just take large filter size, so you can learn better combination to get that 32 numbers.
Okay, thanks. I think I got the intuition what you're trying to explain. Thanks for that.
Okay.
So I have one question.
Yes.
So just when you were saying actually there were 27 numbers, I didn't get that 27 part.
Okay.
When you're using a 7x7 filter, I thought you're looking at a 7x7 submatrix, right?
Yeah. Okay. So this just I took the screenshot. So initial part, 7 was not there. Assume 7 is not there. You have only 3 by 3 kernel, and the depth is 3. So you have 27 inputs. Okay. So this 7, you just forget about the 7 and just say 3 by 3 kernel with the 3 channels. So you have 27 numbers.
You have 27 numbers, and what is the total number of filters you're using then?
In first layer, generally we use 32.
I see. Okay, that makes sense.
In 7 by 7, you have 7 into 7 into 3.
Okay.
Yeah.
That is way higher.
Right. So you're reading, so that you might be learning a very complex feature. So you're not just learning the identity mapping or something in through those kernels. Because from 27 to 32, you can generate by just giving 111 and then 000. I don't know. I mean, just thinking. So it might be happening in that way. So what we want a bigger. And what I read somewhere, like since in initial data, I mean, first layer, we have image has a lot of information. Okay. So we want to capture that information. So this ROI, basically reason of interest. So in the next layer, since you have 3 by 3, but still your ROI will be 5 by 5 or 7 by 7, or it keep increasing, right? So that's the reason you want to use a bigger filter size, which will increase ROI for the image. That is one of the reasons that I've read. So that because in the next layers, you automatically going to have a bigger ROI. And second advantage of using a small filter in the next layers, so that you can have less parameters rather than using more parameters.
I see. From my understanding, I thought for 3x3, like compare 3x3 to 1x1, 3x3 is more expressive. So the bigger the filter size, like if you go for 7x7, it's more expressive.
Right.
But also 7x7 means more computations. So
yes, that's true. So since image has a lot of information, the first layer has a lot of information, we want to extract as much as we can. And why we stop, so like in BGG, what they did, they made every filter 3 by 3, because they said if you have 2 layers of 3 by 3, it's basically same as having a 7 by 7 filter. But what we're going to have, so if you're going to have 7 by 7 in the first, because you have more information, and according to Jeremy, you might be learning a better representations.
Okay, makes sense. Thanks.
Yeah. Okay. So we just ran this and we got so here we are passing a recorder as a callback. So that's the reason we need a callback handler, because now you see we are passing so many callbacks, one callback and the second callback. Again, partial came because this average stat callback might be needing more parameters. So we're passing first parameter directly, and then other it will automatically take while calling the callbacks. So we see we are reaching in one epoch around 68% accuracy, and its wall time is 3.66. And since I don't have CUDA in this machine, so I didn't run it, but Jeremy told how to use the CUDA. So one way, simply you can define the device. So towards the device, if you have multiple GPU on your machine, then you can give the number 0, 1, 2, 3 in sequential order. If you have only one, default it will be 0. And then what we are saying, while initializing that callback, you want to just you give the device a same device. And this is the PyTorch method. So what we have to do, we have a model onto the GPU, we have to put our data onto the GPU. So what we are doing during the fitting, we are putting our model into the GPU. Also during the batch, we are putting our X and Y on the GPU. Okay. Another way, instead of just doing this thing, two device this thing. So what you can say, you can just globally define our device is CUDA, and then you just say model on CUDA and model on data on CUDA. If you want to do on CPU, you can say .cpu, or if you want there, you can just say .cpu or .cpu. It will come back, data and model will come to your CPU or machine. So we appended that callback. So we had already had two callbacks here. We appended one more callback, and then we ran the model. And
Niraj, I have a question really quickly.
Yes.
What? Okay, there's two definitions of CUDA callback, and the first definition has an initialization line, but the second one doesn't. So why is that? Why is there's two versions of CUDA callback, and why is the second one missing an initialization line?
So here what is happening, we are attaching that device to the particular callback. So we are saying, okay, we are defining the device, and we are here, if you see, we need device. Okay. I think there is some error. It should be server device. It should be server device. Yeah.
Yeah, I think I see what's going on here. The second method is a different way of setting the
device. So it is globally set. Yeah.
Yeah, and so after that, after torch CUDA.set device, you don't need that anymore. So that's why.
Yeah, we don't need that parameter basically. So that was a mistake. I didn't run it, so I didn't know the error. So yeah, so there's error.
Thank you.
Sure. So here, if you see with the CPU, it was 3.66 for one epoch, and here for 3 epoch, we are just getting, it's faster than a CPU, and we are not seeing 10 times fast or something because our model is very small. We have very small data size. I mean, not data size, the image size. So for the bigger networks with the bigger layers, we'll see the more, because GPU will do the more matrix multiplication. Here, GPU didn't get that chance. So, but it is still faster, right? So again, as Jeremy like to combine things together. So since we are using con2d and ReLU again and again, so rather than calling 2 times, so what we can do, we can create a function. There it will just take our con2d and the ReLU. So we just, when we call con2d, it will automatically going to apply the ReLU. One more thing. So since we use the Lambda function to transform our images to 1,28,28, we can create our class. For that, we can again we can create a new callback. What it will do when we start the batch, just transform it using whatever the method you want to use. So here we're using a function. Here we're using a function as view transform. So it is going to transform your data into 28 by 28, 1. So okay, and here we can see whatever we have learned, creating a function inside a function, right, and calling using a partial. Now, and one more thing is, so we have used here adaptive pool 2D. So we have taken care of this part because now we have created our callback. So when somebody will give me a different data size, I'll just use our function and it will run my model without to call MNIST tree size. Here I don't have to worry about anything because in the output we are using adaptive average pool 2D. So, and we are saying the output should be 1 by 1. So what it's going to do, it's going to, whatever the output we are going to get, I think we are going to get here 2 by 2, 32, 2, and the output will be 32, 1, 1. So it's going to take the average of whatever the height and width there in the output activations. So that's the reason we don't have to worry about our adaptive because output size. So now what we have defined, we have combined the whole model into CAD CNN layers. Here it will just pass the same function again and again. And as I've told you, initial layer will be having a 5 size kernel, other layer will have a 3 size kernel. Then we'll have a adaptive pool 2D. Again, the flatten, since we are getting output as 32, 1, 1, we want to remove that 1, 1. We just want 32. So that will be done by flatten. And then we have a linear layer that going to have a previous number of activity, and the output will be the 10 classes in this case. So that will be a linear layer we are going to pass. So we got our CNN model ready in one line. Again, we'll call the same runner, and as you can see, we are getting, we have the same model, whatever defined, 5 by 5, 3 by 3, and then we got our results. And we got up to 95 accuracy. Okay, now we want to see what is happening inside a model. How to do that using callbacks, but Fast.ai callbacks cannot do that because the way we have defined our callbacks after the batch, after the fit, or before the fit. So we cannot go inside the model. So we have defined a new thing, hooks. So what we are doing here, if we are defining a sequential model that is inherited from our PyTorch NN model class, we are defining initializing to empty list as equal same as the number of layers. Now, as we know, when we call the forward method, when we write a model bracket, it basically call this dunder call thing, and that call the forward thing. So directly we are overwriting the call thing what was there in the NN module, and in that we are saying while you are applying this module, just keep giving me the mean and standard deviation appending into my list. So that will keep happening the moment I'll call my sequential model. And everyone got this point, or any question?
Yeah, so basically we are calculating standard deviation and a mean after every layer.
Yes.
So we have convolutional, and then we have a ReLU, and then another one. So for every time it goes past through a layer, we calculate and then appending it into this list. Is that correct?
Yes, and just thing I want to highlight is we are not writing a forward method. So if you see, there is no forward in this thing because we are writing call. So that's I just wanted to say, because when I was reading this first time, I thought why there is no forward. So we just overwrited the call and we are doing our forward thing.
Is there any reason we are doing a call here rather than a forward?
I'm not sure anyone knows the answer, but I just know I'm not sure why we are doing this way. Anyone know the answer? Then
anybody else?
I think forward will also work in this case. Okay, fine. So I think I'll try with forward and see.
All right. Thanks.
Okay. So why we're doing this? Because we wanted to see how my activations inside the layers are working. Okay, so what is the mean of my activation for each layer, and what is the standard deviation? So again, so here, if you see now, your question was like, why when we say variance should be 1, answer is standard deviation should be 1. You can see here we are checking the standard deviation. So we always want our standard deviation should be 1 and the mean should be 0. Okay, so now when we see this, okay, so this is the original Jeremy when Jeremy ran and when I ran. So what he was saying, if you see, this is the first layer, and this is the means, and this is the last layer. So what is happening? These activations are going to very large value. So since it is a ReLU, okay, so the mean cannot be mean cannot be 0. We are using ReLU as an activation function here. So it will be always more than 0. But what is happening is going too high. Okay, we don't want, and then it's coming down, going too high and coming down. And also the mean of the other layers are small. So what Jeremy was saying, what must be happening here? We should investigate that, and why it is happening, and why this is happening, and what is happening. We should investigate that. And similarly, in the standard deviation, we wanted 1. Initially, there was no 1. It was near to 0, and slowly they ramp up and they reach to some value. But there was this jump and come down, jump and come down. This we want to investigate. And here you see, if we just take the 10 activation of the first layer, for all the layers, 10 activation, we see for the last layer, the mean is almost, 0. I don't know why it is coming negative. So mean is always 0, and that is not a good sign, because my activations are 0. They are not learning anything. They have not learned anything basically. So I don't want this situation basically. I want that the mean should be high. And again, Again, the variance, if you see variability in that, again, that is also very small. Sorry, variability is very small. And ideally, we want that should be around 1. So here it is 0.35. For the first layer, it's fine. But after each layer, as we are using ReLU, and we know in PyTorch, they use a factor of square root 5 that made thing worst. And that's the reason their variance is, or standard deviation getting reduced each layer by layer. So
one question, could you go up a bit? Just down. The third, yeah, here. So this one is the plot for a mean.
Mean for each layer, 10 activations.
10 activation. So we are saying on layer 0, we have mean of like
0.175.
0.1.
Yeah, right.
So that's too high, is it?
It's not too high because in ReLU you cannot, I mean, you cannot have, already ReLU is, I mean, shifted function, right? So mean will be, I mean, around 0.5. So it is not high. Main problem is here. So it is just, main problem is a 5th layer.
Okay.
So it should be near to 0.5 in one way because this is ReLU function, right? So our mean should be in the linear side, something like that. I mean, half will be 0 and some will be positive. So it should shift to 0.5. But here what we are seeing that this is, I mean, this is 0. I mean, it is not activated at all. So this is a problem. This is not a problem.
Okay. So 5th layer is a problem.
Yes, because as the layer progress, what is happening, it is, I mean, half of the activation getting 0 and slowly after end, you'll see the situation where mean is 0. And the problem with, because of that, what happened during the back propagation, you're going to multiply those X. Basically, you're going to multiply those activations, right? So your variance won't back propagate. So the 5th layer itself, they'll become 0. Because you calculate the error, you calculate the gradients, multiply with the activations to calculate the change for the next layer, and there your X itself is 0. So what you will back propagate? So you cannot learn things.
Okay. And that's where the case of, I think, the normalization comes in, that every layer
different batch norm will come, and also initialization. Why initialization is so important?
Okay.
Excuse me. Any idea why the mean is less than 0? If it's a relative, you should never see mean less than 0. So I don't understand that.
I'm not sure. We have to see the 5th layer is a linear layer.
That's actually the 4th layer. We're not seeing the 5th layer for some reason. It's you see, there's only 5 trend lines there, and so the 5th layer is missing.
Yeah, 1, 2, 3, 4, 5, and there's 6 legends.
Yeah.
So I think I change the legend to 5 and see.
It could be that one of them is superimposed over the other one. I don't know.
Oh, okay. Or maybe you have only 5 layers. It is just range is 6. So its legend is coming 6. So what I'm trying to say is like legend can be like, if you put 10 here, it will give the 10 legends. So that might be the case. There are no, because if you see here in the hook, how many layers are there that I have to run and see?
Oh, okay. So if you put 5 layers, then
1, 2, 3, 4, 5. I think you have 6 layers. Yeah, you have 6 layers. You have 6 layers.
Oh, okay, there are 6 layers. So
try putting 7.
It's 7. Yeah, using flatten, right? If you use a linear layer, then it's 7. If you just go till here, it will be 5.
No, I'm saying in the range, if you can put 7, maybe you will get the 6 layers.
Okay. Range will go from 0 to 5. Okay. Sorry. No, I think I have to run again something. So I have to run again. I don't know where it is. Some activation means. So, okay. No, I have to run the full notebook. Sorry. Okay. I'll run it and check it.
Okay.
So since we have defined our own hooks, PyTorch also give us this functionality. They have called PyTorch hooks. So for that, what we have to do, we have to define a global list rather than passing that list inside a function. We are, defining inside our call method. We are just initialization function. We are defining a global list, and this module need 3 input. This hook need 3 input: module, input, and output. And our append state need 4 input. That's the reason we have to use partial. So partial will going to pass one input first and then 3 inputs automatically. The method is registered forward hook. So what's going to happen? There are two methods, registered forward hook and registered backward hook. So while going forward, it's going to keep whatever function you want to apply. So we'll see what function. So we are applying this append state. So basically we're going to get the data and we're going to do the mean and the standard deviation, going to save into our global list. So we are going again seeing the same thing, going down, going up, going down. So we are getting the same result. Now results are not exactly same because Jeremy had this, I had this, because they are getting initialized randomly. So that's the reason they have a different thing, but more or less behavior is same, going up and going down. So basically it is getting very large rates and then coming down, going large activation. Since we are going to use hook again and again, so we are defining the hook class. One important thing, since here it is going to save our those intermediate activation into the list, and so once the purpose of hook is if whatever you want to do with the hook, you should remove the hooks. Otherwise, what will happen? It will keep eating your GPU memory, and it will just crash. So that's the reason we have a method called hook.remove. So what Jenny was saying, when Python try to remove something that you're not using, so it look for a dunder delete, dunder del, and there we are just calling the self.remove. So basically we're removing the hooks. And if you see here, for registered forward hook, we are passing the partial again because append states need 4 input and our register forward can give only 3. So that's the first one thing we are passing as a self. Self is basically passing the object of my hook class. So I'm passing my object of this hook class to this register forward hook method. And here I'm just I'm just checking whether my hook has this attribute called stat. Since it doesn't have, it has only 3 attributes. So it will create the empty list and then it's going to append my mean. So I get my hook class and again I ran the same thing. So I'm calling the hook object for number of layers that I have and getting the same behavior going up, going down. And since we are running this hook for 4 times and we don't want to do this thing again and again, so let's create the big hook class. There we can have a multiple hooks rather than only having one hook. And what it's going to do, it's going to call my hook, whatever the class that I've defined, and just pass as a list. So instead of doing that thing outside, whatever I was doing here, I'm doing inside my hooks class, right? One more thing, this hooks class is getting inherited from the list container. What is list container? That class that we have defined from the scratch. It has all the methods that generally a list has. When we create a list, when we do the get item, so we can pass here so many things. We can say, okay, if you're passing the integer, just give me that item. If you're passing the true or false booleans, just give me that thing. And if you're passing the slice, so same thing what list does. You method iterator, because so that if we can use it in a for loop or as iterator, we can set the item, we can assign the things, we can delete the item. And how we want to represent our list, we are representing in this way. And if it is a more than 10 items, we are going to represent with 10 ... So that's the way we have defined our list container class. So now our hooks can do all those things what our list container class can do. So if you want to just pick out one hook from lot of hooks, you can just give the index of that hook. So if you see here, it has created total 7 hooks because we have total 7 layers, I think, including flatten layer. And if you run it again, yeah. And one more thing here, what we have done, we have defined enter and exit. So as we have seen in TensorFlow or in while file handling, we use with open or something like that. So when we use with, and it will look for the enter method and it look for the exit method. So while entering it, we are just returning the object of the class, and while exit, we are removing the hook. So that's the reason we are using with And it's very important. It's very nice because you don't have to remember whether I have removed my hook or not. So it's better to use with the with, and we can use using enter and exit. Again, we're getting the same thing. And here what we're checking here, this is a top 10 activations, mean, standard deviation, and mean. This is for all, this is 10 activation. This is a mean of each layer with each iterations. Now, okay, so that is same thing. But that's fine. But why this is happening and what is happening? So what we have done, we have append one more stat into our hook class, that is histogram. And while plotting that histogram, we are so this is a if you see, this is we are plotting for 4 layers, okay. And this histogram is showing the same thing. Your activation going up and going down, going up, going down. So same trend in terms of histogram we are seeing. So more of the activations are going up and going down. And this is the value. So yellow is representing a value near 0. This is a basically color is representing the value. So this much activations are 0. So let's see how many activations for each layer are 0. So how Jeremy did that? So he just flattened. So for all the 4 axes, he just took the here. So he just took 0 because we were using ReLU. So he took 0, 1. 0 and 1 to value till that is less than basically 2 minimum value and divide by the total sum. Okay, so you can see around 90% of the activations are 0 for layer. This is 1, 3, 4. So yeah, so 90% activations are 0. So our convolution network, though it is 95% accurate, but it is not. I mean, half of my activations are not learning anything. They are just 0. So this is a ratio of the number of value that is less than 2 or less than 1 or whatever the minimum value, initial values, and divided by the total number of values. So what we can do, we can define our own value that we have learned in our previous class. One thing that since we can use a leaky ReLU where we have instead of 0, it can be 0.01 or very small value. Also, we can subtract the mean. So we have defined generalized ReLU here. So what we are saying, if you want to use a leaky ReLU, you can use a leaky, okay, or otherwise you can use the whatever the ReLU you want to use. And here we are also saying one more thing, maximum value. So we don't want to go beyond some value of the ReLU, so that we are defining the maximum value. Also, we are subtracting a number, whatever you want to subtract, so that our mean now can be 0. And when initializing this model, he is using instead of 0.5, 0.4. The reason that he was saying, because since we are not using leak as 0, we are using leak as 0.1. So it's better rather than using 0.5, we can reduce the number by 0.4. And we are saying our maximum value can cannot go more than 6. So any doubt till here? Because that's the ReLU we have defined, and we can play with this ReLU we might get different results. Okay, so I think no doubt. So when we do that, now that what we are seeing here, the standard deviations are going, I mean, they are nice. They are like around 1, right? And that's what we wanted. Second thing is, now our mean okay, so now since it is shifted ReLU, okay, it's so our mean should not be 0.5, it should be around 0. And that we are seeing, so it is nice that we are getting. So something we learned, I mean, it improved our model because we have shifted and we are using leaky thing. And when here again, now we can get negative numbers or negative activations also, because we are using we are subtracting the minus 0.4. And when we count this 0, now while counting here, we are not just counting from 0 to 2, we are taking the middle values, because this has a negative value and maximum values. And here we can see only 20% or maybe 30% activations are 0. So that's a nice thing. So we have now instead of 80% or 90% activations are 0, now I have only 20% activations are 0. And when I run this, when Jeremy ran this, and he got accuracy of around 98.2 in 8 epochs. So the homework, we should play with this and try to beat Jeremy by choosing the different parameters, whatever he has passed here, different parameters or whatever way you want to play with this, your generalized ReLU. So that's a homework for this notebook.
Hey Neeraj, one question. Could you go down below the graph here? What's this? Which you see the pinkish line? What's that line? What is this? Actually, it's quite separate in all the 4 graphs.
I think that's which color. This is might be a 5th layer, pink color. This is a pink, so it's a 5th layer. So I don't know why it is happening. I have to understand that. I haven't not given a thought about it. So, but yes, it has a weird behavior. And same thing, if you see something was weird in, I mean, there's first of all, these graphs are random. Sometimes you get some other thing. Yeah, but I understand, try to understand why this is happening.
Okay, no worries. Just one quick question from the chat window. What is adaptive average pool?
Okay, so what is so what's going to happen? We want to make our model image size agnostic. So you might have you might have seen sometime our Inception model used 229 or I don't know 290 or something, and ResNet used 224 or something. So what they do in the last layer, when you get the last layer, so you assume you get the size 8 by 8 comma, assume you have filter as 32 comma 8 comma 8 as the last layer output. Or you might get 32 comma 4 by 4 or 32 comma 5 by 5, right? So what average pooling will do, it will take that 4 by 4 image and it will ask you what size you want. In our case, we say we want only size of 1. So it will just take the average of all the 4 activations and give you the 1 output. If it is an 8 by 8 activation, it will take the input of 64 and give you the 1 output. If it is 16 by 16, it will take all the 16 and give the as 1 output. So it will just take the average of whole channel. Basically, if you give me the, if you ask for 1 output, if you ask for 4 output, I mean 4 by 4 output, it will just take the average and give you the 4 by 4 output. So what is happening here, whatever the size of input that will give you the different size in the output layer, but because of the global average pooling layer, you're going to get the same size after the global average pooling layer. Did I answer that thing?
Yeah. Okay. Thanks for that.
Okay. Yeah.
Go ahead. There is no other question from a chat window. So guys, you can unmute yourself and ask if you have any question.
Okay. So next thing that is very important is batch normalization, and there's a very nice paper. In the nice paper, what they did, they said, okay, as we know, in the last lecture that Jeremy was saying, they claim that it is going to shift the covariance. It's going to avoid the problem of covariance shift. It is not nicely explained in the paper, but really what was happening because of the batch normalization, it is smoothing your loss function. Okay. So if you see the problem, what is happening, since you're doing a training in different batches. Okay. So what might be happening is like that batch is shifted into in that plane, and the other batch is shifted into some other plane. So everything is shifted apart, and you want to bring everything into a same mean and the same standard deviation. So what you will do, you'll subtract from you'll bring the best way to do this, bring it to the 0 and standard deviation of 1, right? So if you bring everything into a 0 and standard deviation of 1, everything will be in the center. And then we are telling the neural net, okay, if you want to shift it a little bit, it's up to you. We are giving you that flexibility. But first we'll bring everything into a center so that and because of that, what is happening, our loss function is getting smooth. And if you see what we are trying to do, we are trying to reduce our loss function with respect to all the training example. But the way we are doing is we are reducing with respect to a loss function for each batch. So we are just expecting while doing that, we are going to do that. So that was a problem we were getting, and this batch normalization was able to solve this problem and make the convergence fast. So what we are doing, we are going to take our activations, calculate the mean for that batch. We are going to subtract the mean and going to calculate the standard deviation. And then we are going to normalize using subtracting the mean and divide by the standard deviation. And that we generally add small epsilon to avoid if you have a zero variance to get, so we won't get the very high value for the normalized value. Now this is still here, we are just bringing all our activation to center a 0 and standard deviation 1. Now we're giving the flexibility to our neural net. Okay, it might not be the best place, you just shift it whatever the place you want to shift it, and we're multiplying with a gamma and we're adding with a beta. So that that's basically a batch normalization. So we calculate the mean for each channel for a batch. So those that many means we will having. If you have C channel, you have a C means. Okay. So we'll implement that into our batch norm. So first thing we'll do, we'll implement use from scratch, and though it is not basically from scratch because we have not wrote our backward pass, we are just using the PyTorch backward, but it's better. So if you see, oh, that's the basic thing, just we are running and we're getting some accuracy. This is our custom thing. So what we need, so Jeremy don't like a Greek letter, so instead of writing gamma and beta, we'll use add and multiplier and the addition. And since this beta will be like a bias term, so what we do, we just multiply our activation with our weight matrices to get and then we add some bias. So we won't use that bias because this will also serve the same purpose. So that's the reason we'll see that we are not going to use that bias. Now these things we now know. This is the gamma, this is our beta, and these are epsilon, the epsilon that avoid the mathematical instability. And we'll go talk about the momentum term. So now we can define a variance and mean also as a parameter, self.var and self.means, but Jeremy used the register buffer. He told two benefits of it. First thing is, while saving the model, we want to keep your variance and means together. So when you save your model, it automatically save as a way when you define in register and buffer. And also while loading to the GPU, it will automatically do when you define with the register buffer. So that's the reason he is defining vars and means in register buffer. Now it's very simple. We just calculate the mean of a batch. We'll calculate the variance of a batch. And if you see the dimension here is 0, 2, 3. We are skipping the 1. 1 is basically a channel layer, a channel dimension. So we are calculating the mean along the batch axis, height axis, and the input and the width axis. So we are going to get the total number of means will be equal to number of channels. And that is in the case of CNN. If you're going to take the case of feed forward network, you're going to have a same number of hidden units. So number of hidden units will be equal to number of means. And same the variance. And okay, now one more thing. This is doing the training, right? So now during the testing phase, we might not have a 10 images. We might have only one image for testing purpose. So how are you going to calculate the mean of that? So what in the paper they have suggested that is, so you can use, we have learned already a momentum method, momentum optimization. Okay, we might have so momentum optimization or any exponential smoothing. So what we can do, we can, instead of taking the moving average, what they do, they just start with like this is the momentum parameter that I was talking, 0.9, and we take the previous value and we just multiply that with the momentum parameter, and then we add the new value with this 1 minus alpha. So that is called exponential smoothing. So because of the new point, it won't get affected that much. It will just keep depending on the previous value. Why we call it exponential? Because if you write it then mathematically, what you'll see at this point, the effect of this will be exponentially less than this. So that's the reason we call it exponential smoothing. And this variance we're going to use for our test data set when we're going to do the prediction or inference time. So that's, and in PyTorch, we have linear exponential, I don't know what is the full form of this. So we are going to do save that into the means and vars so that we can use it during the test time. And then just doing the training, we are just what we're doing, we're subtracting the mean as we discussed, we're dividing by the variance. So here you use the variance because we are going to take the square root later, right? So here we have not used the standard deviation, and you should not use the standard deviation here. So now, then this is the same x multiplied with the gamma plus beta, or addition and multiplication. Same R model, basically number of paddings, strides, and two strides always, and these things. So the same thing. And if you see here, as I was telling, we are not going to use bias now because already we are using beta or addition as a parameter, and both are going to serve the same purpose. So we don't need bias now. So why to use one more extra parameters? So that's the reason we are not doing bias. So now when we use this and using hooks, and now we can see a nice variance and nice mean. So this batch normalization basically has removed all those fluctuation that we were getting. And in one way we were saying the loss function is getting smooth. Now I don't know the reason of this, why this is coming in the end. And Jeremy also, I think, didn't explain this, why this is happening. So any question in batch normalization? Because we use it a lot.
Nothing on a chat window. So again, unmute yourself if you have any question, guys.
Okay, fine. So instead of using our custom batch norm, we can use PyTorch batch norm. So PyTorch has batch norm. And one thing in PyTorch that is weird is, like, rather than, so we define the momentum as a previous value multiplied by a momentum parameter plus the new into 1 minus alpha. Here they interchange the things and they defined as 0.1. So basically it is 1 minus alpha they have defined. So this is the way we have to pass in PyTorch. And when we run it with the scheduler, we are getting accuracy of 0.987. So good. Now, what's the problem with batch norm? One problem that he has explained is, one is because of the small size. When you have a small size, so your mean and variance are very unstable. So because if you have a batch size of 2, so you're going to calculate the mean and variance for each batch separately, and they are going to be very different. And that makes your model unstable, and that won't give a good result. So that's a one problem. And another thing that he is explaining during the RNNs, since we are having the same weight again, it's we are not getting good result with the. It's very difficult to define the batches because your size is your batch, not batch size. Your length is changing, and you're inside. You're doing the for loop thing. Because if you have 10 words, you're going to do the for loop for 10 times. If you have 20 words, you're going to do the for loop for 20 times. So it will be very difficult to define that fixed means and means and variance. So that's the reason there are two problems with this current batch norm. And we'll see how we have able to solve some of the. First problem. There's a lot of papers. So one paper that is layer norm. So what it is saying, rather than doing the batch norm, we can do the layer norm. It means instead of calculating the means and variance for across the batch and the height and weight, just calculate the if you see across 1, 2, 3. So you can calculate across the channel. So you take one image, take the mean of that. Take another image, take the mean of that and variance of that. So they calculate the mean. So now here the number of means and the variance will be equal to the batch size. And in that way, they were getting some results. So, but this was good when you had a small batch size. But if you see the results are coming good for not coming good, I think something, yeah, for 0.8, it went NaN. So according to Jeremy, it didn't solve the problem. Another paper was instance normalization. So here what they're saying is, forget about the channels also, just take the mean across the height and width. So now you're going to have number of means will be equal to channels multiply the number of and the batch size. And another paper that was a group norm. So basically this paper, it nicely explain all things. In batch norm, we are taking the across the batch, n is the number of batch size basically. In layer norm, we are taking across the whole image, C and HW. In we are just taking our height and width, and so we are going to have so many means and thing. In group norm, you can select you want how many channels you want. So they have some idea like, okay, I don't want the mean of all the channels to be same. I want the mean of some of the channels should be same. So and based on the problem, they just figure it out. Okay, if I take the mean of these channels together, I might get the better result. So group norm, basically instance norm and the layer norm is a special case of group norm in one sense. If you take this as one, it become instance. If you take as same as a channel width, it become the layer norm. So in the PyTorch, you can use the same group norm, just passing the different number of channels. So one if you want, or the total thing. So it become instance norm or the layer norm. So yes, so that was the lecture. So any doubt? Because that's yeah, and there was a homework like you have to run this patch norm and try to beat in one epoch what is the best you can get, or the best accuracy you can get in only in one epoch. And Jeremy was able to get around 97. So in one epoch, how much we can reach. So that was a homework for this notebook. So any doubt? And we can play with different batch now if you have any idea or how can we do differently. So you just do the experiment and play with this notebook. And this instance norm was given by Hinton. I mean, not instance, I think layer norm, yeah.
That's great presentation, Neeraj.
Oh, thank you. So, any
I'm
question?
not sure we're bang on time to finish. Was there? I'm not sure if there was any presentation aligned for this week.
I have no idea.
Okay. I think we are bang on time, just 1 minute away from finishing our 90 minutes. So okay. Any question, anybody? There is one question on the chat window. What is the intuition behind using batch norm after FC layer?
Okay, so people have tried before. You mean FC layer? Where is it? FC? Okay, you mean sure. Okay. You mean in a feed forward network? You're saying?
Yeah. Feed forward. Yeah.
Yeah, so this patch norm, this problem is not only with the convolution network. It's a general problem because what is happening, we are training in each batches. So in our loss function, if you see the thing that you want to minimize for the whole training data set, right? But what we are doing is instead of minimizing for the whole training data set, we are minimizing a loss function only for a batch. Okay, so what is happening? Our gradients for a batch will be something, and it will shift our activation to some point, some place in a space. For the different batch, what will happen? You have a different gradients, and it will shift that batch into a different place. So now what is going to happen? All the activations maps are in different places, and I want to bring everything into a same place. So this problem is not with images, it will be with each and every architecture, because after ReLU and all those functions, or sigmoid and all those things, they're going to shift your activation in place, in different plane. So that's the reason we use in every architecture batch norms. And one more advantage of this is it gives a little bit of regularization, because now you have introduced a noise into your network, so you will get a better result, a more generalized result. So that's the reason you can use big learning rate, because you can generalize better. And because of this, effectively it has make our loss function very smooth. So it doesn't have to be on CNN. It can be RNN. I mean, in RNN it's difficult, but on feed forward network or in our convolution network. So any layer you should use it.
Okay, brilliant. Thanks very much. Any other question, anybody? We are bang on time. If not, then we'll close out. Okay, looks like no questions, so we can close out. Neeraj, thanks again for an excellent presentation.
Thank you. Okay, bye.
Okay, bye-bye, everybody.